Hi everyone, thanks for coming out. I'm very happy to introduce our speaker, Robert Andrews, who is a William T. Tutt postdoctoral fellow here at the University of Waterloo. So before Waterloo, did his PhD at the University of Illinois Urbana-Champaign, and then was a postdoc for a year at the Institute for Advanced Study in Princeton. And Robert is interested in computational complexity and in the use of algebra throughout computer science.
All right. Yeah, thanks for the introduction, and thanks everyone for coming to the talk. So today I want to tell you about some recent work I've done on designing parallel algorithms for problems that can be phrased in the language of linear algebra, although these problems don't natively arise from considerations in linear algebra. And everything I'm going to speak about today is joint work with Avi Wigderson. Okay, so we're talking about linear algebra problems, and of course, my favorite problem in linear algebra is computing greatest common divisors of polynomials. So just, it's Friday afternoon, maybe the coffee and sugar hasn't hit you yet, so let me remind you. If we have two univariate polynomials with coefficients in some field, their greatest common divisor, it's just the highest degree polynomial that simultaneously divides both of the polynomials. And the question we'll be interested in this talk is if I give you two polynomials as input, I give you their coefficients as input, what is the complexity of computing the GCD? And when I say complexity, what I mean is the number of arithmetic operations you need to compute this. So we'll be counting operations like addition, multiplication, and subtraction. We won't be concerned with the bit complexity, but I promise I'm not going to play any tricks. I'm not going to abuse this privilege. It's just going to make analyzing the algorithm easier. And why are we interested in computing the GCD? Well, this is a fundamental operation within computer algebra, and it has a number of applications, including to polynomial factorization, decoding of error-correcting codes, and so on. So this is an important problem. What do we know about its complexity? Well, we all know that you can actually compute the GCD in polynomial time. In particular, if you take the Euclidean algorithm and run it on your pair of polynomials, you get the GCD as the output, and a rough, naive estimate of the running time of this algorithm says you use about d cubed many operations in order to compute the GCD of 2 degree d polynomials. You can shave a factor of about d off of this if you use fast polynomial arithmetic. And if you're even more clever and introduce some divide and conquer ideas, you can compute the GCD in near linear time. So this is actually a really nice situation. We have not only polynomial time algorithms, but near linear time, very fast algorithms to compute the GCD. There's also a lot of nice structural mathematics that comes out of the Euclidean algorithm. What more could we hope for? Well, there's maybe one more thing you could ask for with these algorithms, which is, when you sit and stare at them for long enough, you get the feeling that both of these algorithms are kind of inherently sequential. When I run the Euclidean algorithm on my two polynomials, what am I doing? I'm taking one polynomial, dividing it by the other, I get the remainder, and then I do another division with remainder. And I keep doing division with remainder until I get a zero remainder. The last non-zero remainder is the GCD. Right? And you sit and stare at this and you think, well, it's not exactly clear how you could compute the GCD without computing all of these intermediate values. So can you compute this in parallel? Can you avoid that intermediate computation? And if you haven't seen this before, if you haven't thought about this question, the answer might be a little surprising, but it turns out you can compute the GCD in parallel. If you have 2 degree d polynomials, you can compute them, their GCD, using a polynomial number of arithmetic operations and about log squared d parallel time. And if you haven't seen this before, this algorithm is actually a reduction, and it's a beautifully simple reduction. It's a reduction to linear algebra. What you're going to do is you're going to take the GCD, and you're going to express it either as a solution to a system of linear equations, maybe a collection of systems of linear equations. And then what you do is you just off the shelf invoke efficient parallel algorithms for linear algebra problems, like computing determinants, inverting matrices, and so on. And this is how you get these log squared time parallel algorithms for computing things like GCD. And this kind of reduction, it's not necessarily specialized to the GCD. There are other problems within algebra where you can do similar looking reductions to linear algebra. So this is a common design technique for finding parallel algorithms for algebra problems. If you haven't seen this before, I want to give you some idea of what this reduction looks like. So to set some notation, here we have our two polynomials, f and g. F has coefficients fi and g has coefficients gi. And I don't want to talk about the GCD, I just want to talk about a simpler case. I want to understand when two polynomials are coprime. So it's a fact that you can go and prove in the privacy of your own home that these two polynomials, f and g, are coprime exactly when a certain set of conditions holds. And what are these conditions? Well, there's two other polynomials, s and t, so that s has low degree, t has low degree, and you have some interesting identity, that if you look at the polynomial s times f plus t times g, this is identically 1. Now this is nice, but what is it good for? Well, if you sit and stare at this equation for long enough, you realize this is a system of linear equations. What are the equations here? Well, this is a polynomial. So for every power of x on the left and right, you get some equation that says the coefficient on the left equals the coefficient on the right. And this is a system of equations where your unknown values are the unknown coefficients of s and t, and the coefficients of the system are the known coefficients of f and g. So now what you can do is you can just write down this system, invoke a parallel algorithm to solve linear systems, and you get a parallel algorithm to test if two polynomials are coprime. In fact, this system even has a little bit extra structure. It turns out you can solve this system with this particular right-hand side exactly when the coefficient matrix is invertible. And if you write down what the coefficient matrix is, you get this nice structured matrix where the coefficients of f appear in one parallelogram and the coefficients of g appear in another. And you want to test if this matrix is invertible, which is exactly the same thing as testing if its determinant is non-zero. And this quantity, it has a name. This is sometimes called the resultant of f and g. This is a well-studied quantity within algebra that, not only does it tell you something about coprimality of polynomials, but it's useful in elimination theory and, in algebra more broadly. So the punchline here is, if you want to test if two polynomials are coprime, you just need to compute some determinant and check if it's 0 or non-zero. And now you can invoke off-the-shelf parallel algorithms for determinants. In particular, you can compute a determinant of size n using, polynomial number of operations and log squared parallel time. And really what I mean here is there's some algebraic circuit of polynomial size and log squared depth to compute the determinant, where this size is going to be the number of arithmetic operations you use, and the depth is like the parallel running time. So just to make a little more precise what I mean by algebraic circuit, that's the model of computation we're going to use for this talk. So I just want to expand on this if you haven't seen these before. So these are circuits that are built from addition, multiplication, and division gates. And what do? They eat some numbers as input, and they spit out some numbers as output in the natural way, right? If this circuit takes two numbers x and y as input, you can see that its output is going to be something like x squared minus y squared, right? The bottom left gate computes x plus y, the bottom right gate computes x minus y, and this gate computes their product. And we'll be interested in the size and the depth of these circuits. The size is the number of gates, the depth is the longest path from an input to the output of the circuit. And like I said, if you can design one of these circuits to compute whatever value you're interested in, this really corresponds to an algorithm, where the total number of operations you use in this algorithm is the circuit size, and the parallel running time is proportional to the depth of the circuit. So what we're interested in is, are there small, low-depth circuits to solve the problems we're interested in? Okay, so I told you there's this log-squared parallel time algorithm for the GCD, and that's pretty good, but you could ask for more. You could ask for a logarithmic parallel time algorithm. Logarithmic time is about the natural lower bound. You need that much time just to read your input. So can you do better? Well, one idea you could try is let's just find faster parallel algorithms for general linear algebra. So could you, for example, compute a determinant using a circuit of polynomial size and depth less than log squared? Well, we don't know the answer to this question, but it's conjectured that you probably can't do this. And the reason for this, just to give you some idea, is it turns out computing the determinant in parallel is equivalent to computing the trace of a power of a matrix. So if I have an n by n matrix here, what I need to do is I need to compute its nth power and then some, say, the diagonal entries. And how would you compute an nth power of a matrix in parallel? Well, you'd have something like a tree of height log n of matrix multiplications. Each matrix multiplication itself takes about log n depth to implement. So you have this, natural log squared depth algorithm. It's not clear that you can do better than this. Maybe you can, maybe you can't. We don't know. But probably you can't do much better. Certainly you can't get extremely low depth algorithms for general linear algebra. So there's a very nice result from a few years ago that says, in fact, there are no polynomial sized circuits of constant depth to compute determinants, to invert matrices, and so on. So, what I'm getting at here is, why care about this log squared parallel time versus log parallel time? Well, really, it's about some kind of separation between linear algebra and these other tasks that you might be interested in solving in parallel. If you can solve some task faster than log squared parallel time, probably it's a little bit weaker than linear algebra. There's no reduction from general linear algebra to the problem you're interested in. So this is kind of, in some sense, trying to separate the complexity of these two problems. Okay, so the punchline is if you want faster parallel algorithms for something like the GCD, you need to take advantage of the structure present in these linear systems. You can't just close your eyes, pretend that it's general linear algebra and then solve it faster. So let me tell you about the results we were able to get for some of these problems. So here we have two polynomials f and g of degree d, and let's say for simplicity they have complex coefficients. So what we can do is we can actually compute the resultant. This is this structured determinant from a few slides ago that tells you if the two polynomials are coprime. We can also compute the GCD. We can compute these two polynomials s and t that witness the GCD. These are sometimes called the Bézout coefficients of f and g. And we can also compute something called the square-free decomposition of f and g. If you don't know what this is a structured partial factorization of the two polynomials. And we can compute all of these using algebraic circuits of polynomial size and only constant depth. So this is something that you provably cannot get with general determinants, general linear algebra, and here we're able to get actually this very low depth. Yes?
So, for example, for the first thing, resultant,
yes.
it's like a matrix.
Yes.
So you would have this constant depth circuit with many outputs in that case?
So for the resultant, it's a determinant of this matrix. So just one output. But in fact, we can also invert it in the same bounds. So there you'd have a circuit with many outputs.
So this, the polynomials case, that would be a circuit with many outputs?
Yes, yes. So some of these have many outputs, exactly. Yes. In fact, everything aside, the resultant is the only result on this slide with one output.
Okay.
Yes, everything else is many outputs. Yes. Now, there's a bit of an asterisk here when I say these are algebraic circuits, because everything except the resultant cannot be computed by algebraic circuits. And the reason for this is, for example, the GCD, this is actually a discontinuous function of the input. Algebraic circuits, as I define them, they only compute continuous functions. They're using addition and multiplication. So I need one extra operation so that I even have a chance at computing these things, and it's something totally reasonable. We just need to have some kind of branching operation where you look at a value you've computed, and you branch depending on, is this value 0 or non-zero? This is a totally natural thing to include, and with this, we actually get these small low-depth circuits for these problems. But morally, you should think of these as just algebraic circuits. I'll show you later on where this branching comes in. There's one step where we need it.
But they're not, okay, your circuits, to be clear, are not necessarily binary.
Do you mean fan-in too? When you? No, large fan-in.
Yeah.
Yes, arbitrary fan-in.
I thought you wouldn't be getting.
No, if we had fan-in too, we'd get log depth.
Test to side and depth, right?
Yes, exactly, exactly. So these are unbounded fan-in circuits. If you ask for bounded fan-in, we need to pay log depth just to read the whole input.
If you're doing in parallel, then life becomes different. You're sort of fanning in.
Yeah, I mean,
Fine.
yeah. Okay.
I'm confusing your results you're talking about now in our discussions of the last couple of days.
Yes, yes, sure thing. Okay. All right, so any other questions about what the results are? Okay, so I want to tell you a little bit about how you design these algorithms for the resultant and for the GCD. And to do that, I want to completely forget the context of the GCD and resultant and all these problems. I want to forget this context for about 15 minutes or so, 20 minutes, and just tell you how we can do anything at all in constant depth. We'll build up a bit of a toolbox, and then we'll see how it actually becomes useful for solving these kinds of problems. Okay, so what's the first thing you can do in constant depth? Well, really the only thing you can do, in some sense, is polynomial interpolation. So here's the first tool that we're going to use. Say I have a polynomial in many variables. Well, I can always write it as a univariate in one variable whose coefficients are polynomials in the other variables. Right, so here I've written f as a univariate in y. The coefficients are polynomials in the x variables. And now you might ask, well, how do the complexities of f and these coefficient polynomials fi, how do their complexities relate? And it turns out you can relate them pretty nicely. So suppose you could compute f in size s and depth delta. So you should think of this as small size and low depth. Well, it turns out you can get comparable bounds on the complexity of these coefficients. So for example, you can compute each fi in size, say s times d. D is the degree here, and depth delta plus 1. So if you started with a small low-depth circuit, you end up with a comparably small and low-depth circuit to compute all these coefficients. And how do you do this? This is polynomial interpolation. Every coefficient of a polynomial can be written as a linear combination of evaluations. So what do you do here? Well, take the circuit for f and partially evaluate the y variable at d plus 1 points. These partial evaluations, they give you some linear combination of them, will give you the coefficients of f. So you can just include those coefficients in your circuit, and now you have the coefficients of f. So this is the first thing we'll use, and this is really the only thing we're going to use. Everything we do builds on top of this sort of basic construction. So let me give you an example of what you might do with polynomial interpolation. And to do that, I need to introduce one useful family of polynomials for what we're going to do. And this is a family of polynomials called the elementary symmetric polynomials. So these are polynomials in n variables of degree d. And what you do is you sum over the integers 1 through n. You sum over all subsets of size d. And for each subset, you pick up a monomial where you get the variables that are indexed by that set S. Okay. Now, why would you care about these? Well, there are two reasons to care about this family of polynomials. One is what's known as the fundamental theorem of symmetric polynomials. So what is a symmetric polynomial? A symmetric polynomial is just, if I permute the variables around, I get the same polynomial back. So x plus y is symmetric, but x plus 2y is not. Now, it turns out that for every symmetric polynomial f, there's another polynomial g, not necessarily symmetric, such that f can be written as g composed with the elementary symmetric polynomials. What this says is if you have a symmetric function, you can explain the fact that it's symmetric by writing it in terms of these obviously symmetric functions. This is one reason we'll care about these. The other reason to care about them is, well, the elementary symmetric polynomials are really coefficients of univariate polynomials. And what I mean by this is, say I have a polynomial f over the complex numbers. I can always write it as a product of linear terms. And if you expand out this product, you see that its coefficients are really the elementary symmetric functions of the roots, up to some sign that we can handle the sign easily. But really here, the coefficients are these elementary symmetric functions of the roots. And this is a useful perspective that, if you aren't familiar with this, I want you to start thinking in this way, that whenever I give you a polynomial as input via its coefficients, I'm really giving you the elementary symmetric functions evaluated at the roots. That's how you should think of the input. Okay, so now I promised you an example of interpolation. Let me give you that. So there's a very nice result by Michael Ben-Or from the 1980s that says these elementary symmetric polynomials, you can compute them using circuits of quadratic size and depth 3. And if you haven't seen this, this might be a bit surprising, because here you have a potentially exponential number of monomials. If you used a depth 2 circuit, you'd have to pay this exponential size, but somehow going to depth 3, you get this savings. Now you only need to pay quadratic size. And the way you do this is actually very simple. You apply a polynomial interpolation to the product of 1 plus y times xi. If you expand this as a univariate in y, the coefficients are exactly the elementary symmetric functions of the x variables. So this is a small circuit of size n. It's degree n. So you apply interpolation, you get a circuit of n times n size, so quadratic size, and depth 3. And this works for all of the elementary symmetric polynomials. Okay, so that's one family of polynomials we'll be interested in. The other family has a bit of a simpler definition. It's called the power sum polynomials. These are just, I have n variables, I take the sum of their dth powers. Now, why would you be interested in these? Well, an analog of the fundamental theorem of symmetric polynomials also holds for the power sum polynomials. That for every symmetric polynomial f, there's another polynomial g, not necessarily symmetric, so that I can write f as g composed with the power sums. Okay, so in particular, the elementary symmetric functions, they're symmetric. So you can write them in terms of the power sums. And conversely, you can write the power sums in terms of the elementary symmetric functions. So can you make this kind of conversion explicit? And that's really going to be our second tool, is some explicit version of this conversion between the elementary symmetric functions and the power sums. So what is this? Well, I'm not going to show you the identities. You can check our friend Wikipedia for them. The point is there are some family of explicit, I'll say low-depth identities between these families of polynomials, and these are sometimes called Newton's identities or the Newton-Girard identities. Their specific form is really not important for this talk. All that matters is that they're sort of explicit and they're low depth. And what I mean by this is, for example, if I give you as input the power sums, you can compute the elementary symmetric functions in polynomial size and in low depth. Right? What I mean here is, if I give you some, if I have an algebraic circuit taking as input the power sums at some set of points, well, with a circuit of polynomial size and constant depth, I get the elementary symmetric functions evaluated at the same set of points. And the proof of this just uses these explicit identities and polynomial interpolation. And conversely, you can go in the other direction, that from the elementary symmetric functions, you can compute the power sums. And one thing to note is the elementary symmetric functions, they're only defined in degrees up to n, where n is the number of variables. The power sums are defined in higher degrees. And this algorithm lets you get the power sums up to any degree you like. Yes?
So in that lemma, are you given the power sums evaluated, like each power sum evaluated on each point?
On the same set of points. So you have some set of n points. I take the first power sum on this set of n points, second power sum, third power sum, and so on.
You get every pair, okay. And n points.
Yeah, I mean n, say n complex numbers, just to disambiguate what a point is. Yeah. Okay, so these also turn out to be really useful algorithmically in maybe a bit of a strange way, but I want to give you some idea of how you can use these to design algorithms. So I want to give you a couple of toy problems to warm up, and then we'll start making our way back towards the GCD. So the first problem I want to look at is polynomial division. So here we have as input two polynomials, f and g, and we've got this extra promise that g divides f. What I want to do is I want to compute the coefficients of f divided by g. I want to do this with a circuit of polynomial size and of constant depth. So how are we going to do this? Well, for the purposes of analysis, let's write down the factorizations of f and g. Right, f has some roots. Because we're over the complex numbers, everything just splits into linear terms. F has some roots, alpha i's and beta i's. G has some set of roots as well. And because g divides f, the set of roots of g is a subset of the roots of f. Okay, now if we had this factorization, I mean, we'd be done, right? We could just delete all the alpha factors from f, and that would be the quotient. We don't have this factorization, but we can sort of design an algorithm that behaves as if it had access to this factorization. So here's what we're going to do. In the first step of our algorithm, you use Newton's identities to compute the power sums of the alphas and betas and the power sums in the alphas. Now remember, the coefficients of f are the elementary symmetric functions of its roots. So when I give you the coefficients of f, I've given you the elementary symmetric functions in the alphas and betas. So in polynomial size, constant depth, you can get their power sums. And likewise with g. You get the elementary symmetric functions in the alphas as input, so you can compute the power sums in the alphas. And now what are you going to do? You're going to use the power of subtraction. If you subtract these two power sums from one another, well, you just get the power sums in the betas. And now, use Newton's identities to go back to the elementary symmetric functions. The elementary symmetric functions in the betas are exactly the coefficients of the quotient. So all these steps can be implemented in polynomial size, constant depth, and I only have a constant number of steps. So we're done. So this is kind of like getting access to some kind of a logarithm. We're turning division into subtraction. Let me give you another example, a bit of a toy problem. One more comment is that this sort of algorithm that you can do division in constant depth like this is not new. Dardiobini and Victor Pan already did this in the 80s. In fact, they did division with remainder. They don't state their algorithm as being constant depth, but if you stare at it, it's clear you can do this. We also have sort of another algorithm along these lines that handles remainder as well. So here's another bit of a toy problem. Now we're just given one polynomial f as input, and we're promised that f is an rth power of some other polynomial g. And we know r. we want to compute the coefficients of G. So what are we going to do? Well, again, we're going to write down the factorizations of f and g. Because f is the rth power of g, every factor from g appears r many, some factor r more times in f. So what do? Well, compute the power sums from f. What do you get here? Well, you get a power sum where each alpha is repeated some r times. So this is really like r times the power sums in the alphas without that repetition. Divide this by r. Now you genuinely have the power sums in the alphas. And go back to the elementary symmetric functions in the alphas. These are exactly the coefficients of g. So again, we're getting some kind of a logarithm. You're taking roots into just division. Okay, so that's a bit of a warm-up. Now let's do something maybe a little more interesting. Okay, so I should mention everything I've said about the Newton identities in low depth, all these sorts of basic ideas about interpolation, all of that is pre-existing work that's been known for at least some 20-ish years. Now we're going to do something genuinely new. So this is the first sort of interesting problem we're going to look at. I give you as input two polynomials f and g. Now to describe the problem, I need to know the roots of f. It has some roots alpha 1 through alpha n. And what I want you to do is I want you to evaluate g at each root of f and then output the sum of that evaluation. Now I claim you can do this in polynomial size and in constant depth. And how would you do this? Well, I mean, you stare at this the first time, maybe you would think about numerically solving for approximations of the roots of f and then performing this evaluation. Here we're going to do this exactly. So maybe by now the pattern is kind of clear. First we're going to do something with Newton's identities. We're going to move to the power sums. So you can get all the power sums in the alphas from the coefficients of f. And then what do? You take this sum, you open it up, and you realize, after you change the order of summation, this is an inner product between two vectors. The coefficients of g and the power sums in the alphas. We have the coefficients of g as input, and we've computed the power sums in the alphas. And now we can just implement this inner product with a few more gates and about 2 more layers of depth. So all of a sudden, we've got this strange-looking object in polynomial size and in constant depth. It's not really clear, like, what is this good for? I don't know an immediate application of this. But now we're doing something where, in the problem description, I can start talking about, problems that involve the roots of these polynomials. And you can think of the GCD as being, easily defined in terms of the roots. So maybe we can build up a toolbox to deal with things like this. So now I want to generalize this a little bit. Instead of putting a sum here, I want to put any elementary symmetric function of these g alphas. And again, you can compute any of these in polynomial size and in constant depth. And by now, I hope the pattern's clear, you're going to use Newton's identities somehow. So what do? Well, first you're going to interpolate out the coefficients of powers of g. Right? You do this for all values of k between 1 and n. And now what do? You use the algorithm from the previous slide. You compute these power sums in the g alphas. And now you use Newton's identities one more time to go from power sums back to elementary symmetric polynomials. Okay, so this lets us compute, something that's maybe nice in general. And I claim now we've actually made progress towards the GCD without even realizing it. And why is that? So I want to go back to the resultant, which is this quantity that tells you when two polynomials are coprime. Right? I showed you one definition in terms of the determinant of a structured matrix. It turns out there's another formula for the resultant. If f has these roots alpha 1 through alpha n, you can show the resultant is exactly the product of the evaluations at g at the alphas. And this should make sense, right? If f and g share a root, at least one term in this product will be 0, so the whole product is 0. If f and g are coprime, they share no roots, so every term in this product is non-zero, and the whole product will be non-zero. But we already saw how to compute this. This is the top degree elementary symmetric function of the g alphas. So as a corollary, we already have now a polynomial size constant depth circuit to compute with the resultant. And somehow we're not using linear algebra at all in this, right? Even though it's defined, one definition of this is as a very structured determinant, you have this other route that gives you these small constant depth circuits. Okay, so now I want to give you a bit of an idea of how you might actually make progress towards the GCD. So first I want to start with a bit of a simplifying assumption. I want to compute the GCD when the case, in the case where the two inputs are square-free polynomials. So what do I mean by this? So I have two inputs, f and g. F has some roots alpha 1 through alpha n and gamma 1 through gamma d. G has some roots beta 1 through beta m and gamma 1 through gamma d. The gammas are shared. The alphas and betas are separate. And when I say the word square-free, all I mean is that all these alphas, betas, and gammas are actually distinct numbers. There are no multiplicities here. If I'm writing two different symbols, I genuinely mean two different numbers. So what we want to do is we want to compute the GCD. Now, I mean, you stare at this and it's really not clear maybe how to start. I have to apologize and do one clever thing. And by clever, I mean I have to do something and I can't immediately explain why I'm doing it. So I want to look at this bivariate polynomial. Here, z is a fresh variable. This is z minus x times g of x. And what I want to do is I want to look at partial evaluations of this polynomial where the x variable is substituted by a root of f. Okay, so for example, if I substitute one of the alphas for x, I get z minus alpha 1 times g of alpha 1. Now remember, the alphas are the roots that only belong to f. They're not roots of g. So this is some non-zero polynomial in the z variable. And likewise for all the alphas, you get some non-zero polynomial in z here, because the alphas are only roots of f, they're not roots of g. On the other hand, if you plug in one of the gammas, well, this g of gamma 1, this is going to be equal to 0. The gammas are shared roots between f and g. And this is true for all the gammas, that all of these evaluations turn out to be 0. Now what I want to do is I want to look at elementary symmetric functions of these lambdas. This is a bit of a, it looks like a slightly different setting than earlier. Earlier we looked at evaluations of one univariate at the roots of another. Now we have partial evaluations of a polynomial in two variables. I claim the same algorithm from before works in this setting. So I can actually compute elementary symmetric functions of these lambdas. Let's see what we can do with them. So I want to take all this notation and just squash it down into the corner. And now let's look at what happens to the degree k elementary symmetric function of the lambdas. Well, we can expand this out as a sum over all the monomials. And we can split up each monomial as a product of lambdas that come from the first n evaluations and the last d evaluations. These are the evaluations corresponding to the alphas, the roots only belonging to f, and these correspond to the gammas, the roots shared between f and g. Now, if I have any term here, if t is not the empty set, I'm going to pick up a 0. So the whole term will be 0, and it drops out from the sum. So in fact, I can restrict my attention just to the sum over the first n of the lambdas. Right? And this is just an elementary symmetric function in fewer values. Right? All this is saying is that if I take an elementary symmetric function and I put in some zeros, they just drop out. I just get it's the same degree elementary symmetric function, but on fewer variables. Okay, so why is this interesting? Well, suppose we knew n. Suppose we knew the number of roots that are unique to f. We don't know that yet, but suppose we did. Well, what is the top degree elementary symmetric function? It's a product. It's the product of all these z minus alpha i's times g of alpha I. Now these g alpha i's, the product of these guys is some complex number. This is a polynomial in z. Let's normalize it to have leading coefficient 1. Now what is this? This is the product of z minus the alpha i's. This is exactly f divided by the GCD. So if we could somehow compute this value here, well, we'd get f divided by the GCD. Divide f by this, you get the GCD back. Well, it turns out, we already know how to compute these things, except I don't know how to find n yet. Right? I don't know how many roots only belong to f and not to g. But, well, you know that, whatever the value of n is, all these elementary symmetric functions are only going to depend on the n non-zero lambdas. And if I pick a symmetric function, say of degree n plus 1, it will always vanish, right? Because in this summation from earlier, you'll always pick up a 0 term if k is larger than n. Right? So really, what we can do here, so this is just saying we have two square-free polynomials. We can compute their GCD in constant depth, polynomial size. What are we going to do? Well, we're going to compute all these elementary symmetric functions. We know how to do this. And then you can compute n as the highest degree of a non-zero elementary symmetric function here. Like I was saying before, if you take this above degree n, you're always going to pick up a 0 in each term of the sum. So the whole thing is 0. On the other hand, at exactly n, you get some non-zero product. So this is the one non-algebraic, non-arithmetic operation, is you need to look at these n plus d values you've computed and find the largest degree one that's not 0. That's all the branching you need. Once you've computed this, you just normalize it to have leading coefficient 1, and you output f divided by this elementary symmetric evaluation. That's the GCD. Okay. Okay.
How'd you get n again?
How do you get n? So you write down all of these elementary symmetric functions. You write them all down.
I was computing n and I was taking log n time.
Oh,
Just a matter of my mind not totally clicking the right way.
yeah. Yeah, I mean, if you're actually doing this in parallel on a real computer, of course, this will take some log n time. Yes?
So right now, the elementary symmetric function has how many varieties? Like these multi-variables?
These?
No, like for elementary symmetric functions.
Uh-huh.
How
In,
many variables are you using?
in,
EK lambda 1, EK lambda.
yeah, so, okay. So these are really elementary symmetric functions, I mean, in one variable in the sense that there's this one underlying z variable? Or do you mean how many of the lambdas are there?
No, how many varieties? So you have Z and also you don't have X,
Right, right, so just one variable.
right?
Yeah. Okay. All right, so that's how you get the, yes?
The complexity of the entries of polynomials are like constant, right?
Sorry, they're what? They're,
Like the coefficient of the polynomials, they have like a
Uh-huh.
constant bound for it.
oh, so I haven't thought about that. I don't think they necessarily have a constant bound.
Yeah, but like how do they appear in the complexity of the width? And like in case like you want to have a very large coefficient.
So I think in terms of, so because this is some low depth computation on top of the input, this in particular means it's some low degree function of the input. And so whatever the bit complexity of your, so whatever the size of your input values are, I think you should be able to show that the coefficients here are at most, they have size at most polynomial in the size of the input. Yeah, so nothing unreasonable, nothing too crazy high. Okay, other questions? Okay, so this handles the square-free case. I want to give you at least a little bit of a sense of how you might handle the multiplicities when you're computing the GCD, right? Because this handles the case where f and g, their factors don't have any multiplicities at all. How might you incorporate those multiplicities into your algorithm? So I claim that even when f and g are not square-free, the preceding algorithm actually does something useful. So here's what the preceding algorithm really does for general f and g. So suppose you have f and g as input, and f factors like this. F has these factors x minus alpha I raised to the power ai. Well, you run this algorithm, and really what you're doing is you're splitting the factors of f into two sets. one set that corresponds to roots of g, and one set that corresponds to non-roots of g. That's really what this, when we had this bivariate polynomial that had a factor of g, that's what that factor of g was doing, is it was used to somehow filter out the roots of f that are roots of g or are not roots of g. Right? So if you just rerun this analysis, but now f and g can have multiplicities, what you really get is you can compute the coefficients of these two polynomials. F, where you only take the factors that correspond to roots of g, and the factors of f that correspond to non-roots of g. You can compute both of these in polynomial size and in constant depth. So this gives you some way to sort of, one way to think of it is f is really like the multiset of its roots. G is another multiset of its roots, and this lets you take intersection and set difference on the multisets. So why is this useful? Well, it turns out you can determine the multiplicities of, there's some definition of multiplicity of factors that's done in terms of evaluation of f and related polynomials. In particular, x minus alpha to the power t, well, this is a factor of f exactly when f and its first t minus 1 derivatives vanish at alpha. Right, and here if you like to think about finite fields, okay, this won't work over very small finite fields. Our algorithms don't work over small finite fields. So we're still working in the complex numbers here. So as a corollary, if you stitch together this observation about multiplicities with this sort of filtering algorithm I showed you earlier, where you're using f prime as the g polynomial, right? This thing that filters the roots of f, you get a result like this. You can actually get out all the factors of f of multiplicity at most 1. Right? These are exactly the factors of f that correspond also to shared roots with its first derivative. Now this is maybe a little bit of a strange way to write this, multiplicity at most 1, and I've still got the multiplicity here. But if you generalize just a little bit more, I won't show you the details, it's not too difficult, you can actually apply many different filters to this polynomial f, and you get a lemma like this, that in fact, from the coefficients of f alone, you can compute something like this. You can get the product of all the factors of f that have multiplicity at most t for some parameter t of your choosing. And this involves looking at f, its first derivative, second derivative, all the way up to the t minus first derivative. Okay, so if we have this, I claim we're nearly done with the GCD. Why is that? Well, here are the 3 steps you're going to run. So first, from your polynomial f, you're going to compute the following polynomial. So just look at the right-hand side for now. I want to get the product of all the factors of f that have multiplicity t, but I want them with multiplicity 1. Now, how am I going to write this down? Well, I can get this as the quotient of 2 polynomials I know how to compute. I take all factors of multiplicity at most t, and then I divide out all factors of multiplicity at most t minus 1. Right? We know how to do this kind of division. Now, this quotient is the factors of multiplicity t, but they've all got multiplicity t. So I want to remove the multiplicity. I want to take a tth root. Well, we saw how to do that too. So now for each t, I can get all the factors of f of multiplicity t, but now with multiplicity 1. And if you're not familiar with this, this is actually this thing I mentioned earlier, the square-free decomposition. This is some interesting structured factorization of f. So you do this for f. You do the same thing for g. Now, from here, we can get the GCD pretty easily. And how are we going to do that? Well, I claim that this is the GCD of f and g. So what do? For all I and j, you look at fi and gj. These are the roots that show up with multiplicity I and f and multiplicity j and g. I take their GCD. Now, these 2 polynomials are square-free, so we know how to take their GCD. And this gives me some set of roots. What multiplicity do I want to take them with? Well, the minimum of I and j. Right? If I have a factor that appears with multiplicity I and f and j and g, I get it with its minimum multiplicity in the GCD. You do this for all I and j, this gives you the GCD. Okay, so that's really all I wanted to say about the algorithm. We have some other things, like I said, you can do Bézier coefficients, you can invert this, the matrix that corresponds to the resultant. And there are some other fun things here. We actually have a slightly different, still constant depth algorithm for the GCD of many polynomials. I'd be happy to tell you about any of this after the talk. So let me just end with a few questions that are left open by this work. So I think one really interesting question here is to look at the extended Euclidean algorithm. Right? When you take the Euclidean algorithm and run it on a pair of polynomials, you get a large sequence of remainders. The GCD is the last remainder in this sequence, but sometimes you're interested in computing other remainders from this sequence. Can you do this in parallel? Well, again, linear algebra gives you a log squared time parallel algorithm for this task. Can you do better? Can you beat that log squared n? We don't know how to do this, and in fact, we have some follow-up work that says you can't get constant depth for this kind of task. And for the experts in the room, if, really I'm asking about, can you compute subresultants in this better than log squared depth? There's a second question here, which is maybe a bit fuzzy, but this work is really about computing symmetric functions efficiently in low depth. And I'd really like to know what other symmetric functions can you compute in low depth? Can you give me some kind of characterization? So for example, if you think about the fundamental theorem of symmetric polynomials, if I have some symmetric function f, I can write it as a composing polynomial g with the elementary symmetric functions. If that g has low depth, the overall composition is low depth. Can you prove a converse? That if f has low depth, does that composing polynomial also have low depth? Can you say something about that? That would be very interesting. We really don't know how to say much here. And then finally, one question which I really don't even know how I would approach this because I'm not much of a programmer. I would love to know if this algorithm is performant in practice. The GCD is a natural thing to look at. Can you actually get something out of this algorithm that might be useful for real world applications? So that's all I wanted to say. Thanks so much for your time.
Thank you. Are there any questions?
You restrict two things to be, your functions to be binary input.
Yeah.
Do we have a better hope of a negative result about log squared lower bounds?
If you restrict to, you mean just fan-in-2 gates?
Fan-in-2.
Yes.
Obviously, we have a better chance, but...
Yes, well, okay. I mean, so one thing I wanted to brush under the rug, but it seems like you're trying to tear the rug off the ground, is if you have unbounded fan-in, you can actually do linear algebra in log depth, but with bounded fan-in. Sorry, with unbounded fan-in. So there are sort of three classes sitting around here. Log depth unbounded fan-in, log depth bounded fan-in, constant depth unbounded fan-in. And we're going from the very top one to the very bottom one. But yeah, I mean, if you use fan-in-2, of course, then the problem actually becomes open instead of...
Is there anything that can be said in multiple variables?
So do you mean for like polynomials?
Multivariate polynomials.
Yes, there is. So for example, I mean, it depends on how you want to represent your multivariate polynomials. If they have the short answer is yes. You can still compute GCDs in constant depth. You just maybe need to be a little more sensitive about what your representation is. If they're in a constant number of variables, just write down their coefficients, that's fine. But if they're in, say, degree n variables, right, the coefficients, that might be hard to write down. But if you write them as, say, small algebraic circuits, you can compute the GCD by taking the two circuits and adding some constant depth circuitry on top of that. And this is in the paper as well.
Chris, have you briefly remind us how FT is computed on the penultimate slide?
Yes, FT. Yes, this thing. So this is what I want to compute, right? I want all the factors that do appear with multiplicity t, but I want them with multiplicity 1. So I didn't exactly tell you how to compute these two guys, right? This is all the factors with multiplicity at most t. Divide out all the factors of multiplicity strictly less than t, right? So now you have the guys with multiplicity t, but they also, in here, they're coming with that multiplicity t. So take a tth root, right? I didn't tell you exactly how to compute these, but if you're interested, I can tell you.
Okay, yeah, I'll take it offline then.
Yes. Yeah, yeah.
Other questions? I have one, which is,
Yeah.
what about just integer GCD?
So that is suspected to not be parallelizable. And our results certainly don't hold there. Even just any kind of parallel algorithm, say better than, I think getting any, something like subpolynomial in n, if you have n-bit integers, getting parallel time that's subpolynomial in n, that's an open problem. And it's because you don't have this reduction to linear algebra that we had in the case of polynomials. Yeah, so I think proving either some kind of p hardness lower bound or getting a better parallel algorithm, both of these directions are open and interesting.
You said there were other problems like the GCD that you could reduce to linear algebra, things from like computer algebra or something like that. Do you have any examples that you're looking at or thinking about?
Yeah, so one example that I would be really interested in is something like Pade approximation. I give you some initial segment of a power series. I want to approximate it as a rational function of some prescribed numerator-denominator degree. This is also a linear algebra problem. You can solve it in this log squared depth. Can you do better than that? It's actually very closely related. It's closely related to this last open problem about the extended Euclidean algorithm and subresultants. That if you could do better for something like Pade approximation, you would also get, there's some sort of class of problems that we're still struggling with, and Pade approximation is one of them.
Any last questions? So just as a quick note, this is the last Tutte Colloquium for the semester, so we'll resume again in the winter. And yes, let's thank Robert again.
Thank you.